What's up geeks, and welcome to the channel. Suppose you are given two integer arrays, pre-order and in-order, where pre-order is the pre-order traversal of a binary tree and in-order is the in-order traversal of the same tree. What you are asked to do is construct and return the binary tree. Okay, before delving right into the solution, let's go through a quick reminder about these types of traversals. For more details, feel free to check the video linked in the card above. So in a pre-order traversal, we visit the root first, then traverse the left subtree, finally traverse the right subtree. In this example, if we attempt to traverse the tree you see in a pre-order manner, we will obtain the array in front of you. However, in an in-order traversal, we visit the left subtree first, then visit the root, finally traverse the right subtree. In this example, if we attempt to traverse the tree you see in an in-order manner, we will obtain the array in front of you. Okay, now that we have these two arrays, how can we, by making use of them, go back to the tree we had? Well, the main observation we can do here is that in the pre-order array, the root is located at index 0. And if we manage to locate this root value in the in-order array, then all the elements to its left will represent the left subtree, and all the elements to its right will represent the right subtree. Additionally, notice that this same logic can be repeated on all the nodes of the tree. So if the root's right subtree contains these three elements, then the first element among these in the pre-order array will be the root of that subtree. And after locating that root in the in-order array, the elements to its left are its left children and the elements to its right are its right children. Now, before implementing this logic, let's attempt to visualize it one more time. So, given these two arrays, we will iterate over the pre-order one in sequence and attempt to find the values we are encountering in the in-order array. When this is done, the elements to the left of that node will represent its left subtree and the ones to its right subtree. This same logic is then repeated on the subtrees we found until no more elements are left and the whole tree is generated. To implement this logic, we must initialize an integer variable to 0, let's say pre-order index, to keep track of the next root element that will be used in the current iteration. Then we will attempt to retrieve this root in the recursive call used to generate the tree. As a start, we will first pass to this method both arrays we have and the full range of our in-order array. Similarly to what we previously discussed, as soon as we retrieve the root value, we need to locate that same value inside the in-order array. We'll do that for now with the help of streams. When this is done, the left subtree of the root will be generated in the same recursive way and will be represented by the nodes ranging from the start of the in-order array to the root index we just found. The remaining nodes, starting at the root index till the end of the in-order array, will represent the right subtree of that root node. Finally, all we must do is return the root. And as with all recursive calls, we need to add a breaking condition. And here, if the range provided is empty, then we should return the null value. That's it, we can now generate a tree when provided with the pre-order and in-order arrays of that tree. But wait, there is a catch. You see, this line of code right here tremendously increases the complexity of our method, because every time we invoke this method, we will have to iterate over the array again in search of that index. Therefore, to tackle this problem, what we need is kind of a store that will allow us to save the in-order values alongside their corresponding indices, and later let us retrieve these values in constant time. And if this description reminds you of maps, then kudos to you. So let's go ahead and initialize a map. Inside this map, we will store all in-order values alongside their corresponding indices. This will be done once and once only before we invoke the recursive method. Now, inside the recursive call, we don't need to iterate over the in-order array again to fetch the root index. We don't even need to pass it to the recursive call. All we must do is fetch it from the map via the get method. That's it, the complete, optimal solution to the problem at hand. Another variant of this question is constructing a tree when provided with the in-order and post-order traversal arrays of that tree. You see, the implementation and approach taken to solve this new problem is like the one we just wrote. However, instead of retrieving the current root from the beginning of the post-order array, we need to retrieve it from the end, because as its name suggests, in a post-order traversal, we traverse the left subtree first, then traverse the right subtree, and finally visit the root. So let's bring back our previous implementation, rename our pre-order input array to post-order, rename the iteration index to post-order index instead of pre-order index, initialize it to the last index of the array instead of 0, and decrement it inside the recursive method instead of incrementing it. The only and last change we need to apply is flip these two lines. Why? Well, because we are traversing the array from the right to the left, and we are starting at index length -1, and the right subtree is visited before the left subtree in a post-order traversal. Therefore, the right root nodes will be encountered before the left ones, and hence the right subtree must be populated first. That's it. Every other single line of code remains the same, and with this you obtain the complete solution to this second problem. The links to the LeetCode exercises we solved today can be found in the description below. Let me know your thoughts and suggestions for upcoming videos in the comments section. And that's it for today. I hope it was helpful. Thank you guys for watching, take care, and I will see you in the next one.